So thank you very much. It's a pleasure to be here. Let me thank again for the organizers for allowing me to be here in this beautiful place in incredible India. We can see the whole range of different. I was in Hampi a few days ago, and it was a really great scenery and heritage. The talk I will give today is in, let's see, I think, no. Yeah, it works. Okay, right. So, okay, good. Yeah, so, okay, so it's originated with discussions with Yasir, who is one of the organizers, and I told him that he cannot be the chairman of my talk, so I think Yogesh or Fakir will be the chairman. No, you are the chairman. Yes, right, okay. You refuse, right. And what happened is that he visited me in Budapest when we talked. I mean, I have my student, Peter Balla, and he was working on some complicated FCC phase diagram with anisotropies and so on, and it was really complicated. And during the discussions with him, it turned out that even the, I need to find the right way, even the simplest FCC lattice is interesting, the Heisenberg model as FCC lattice. So that will be the first part of my talk. And as we follow discussions and our work, I will show what we found out in the Honeycomb and in the case of the diamond lattice. So, first part, ground states of the classical Heisenberg model FCC lattice. FCC lattice is one of the first examples, actually it is the first example, where antiferromagnetism has been observed by neutron scattering. This is a paper from 1951, and first neutron scattering on an antiferromagnet, and Schultz, he got the Nobel Prize in '94 for this and other works. So what you see here, they took a neutron elastic scattering measurement at high temperatures and low temperatures, and as they cooled the sample, it turned out that additional peaks, black peaks, appeared in the spectrum. And this was a signature of the ordering of the magnetic ions in this material. And the ordering is such that the up spins are in the 1-1-1 direction of the planes. So you have alternating planes pointing of up and down spins in the 1-1-1 direction. The 1-1-1 direction is in the direction of the corner. FCC lattice, usually we see the FCC lattice as a cube decorated with the central sides. But from this picture, it is very difficult to see what is the real structure of the FCC lattice. Instead of that, I show you these two figures where it shows that the FCC lattice can be thought of as edge-sharing tetrahedra. This is very similar to the Pyrocle lattice that we have corner sharing. Here we have edge sharing. Or, if you wish, we can think about the FCC lattice as also as edge-sharing octahedra. And it is essentially made out of triangles. And the first neighbor is between the, say, corner side and the side on the center of the lattice. Actually, it is the edge of the tetrahedron. The second neighbor here, J2, is the diagonal of this octahedron. And J3 is the second neighbor in the triangular lattice. Theoretically, in 1950, Anderson already looked at the FCC lattice, and this is from his paper, and I think amusingly I learned it today, that the behavior of the antiferromagnetic FCC lattice below the Curie point is rather complicated, and this is absolutely true. You can see by Davidson equation that the only restriction on the spins is that the sum of the spins on a tetrahedron shall be 0. In other words, we can write the Hamiltonian as a sum of the spins on a tetrahedron, and we square it, and we add this up. So in case, and this is for classical spins, in case that this is 0, this is the lowest possible state, and that will be our ground state. Now, if we have 4 spins of equal length, there are many, many states that can satisfy this configuration. Chris Henley used to play the game, the spin lambada. It means that here you can draw your spins from tail to head, and you have to draw 4 spins, And if you draw it from tail to head, tail to head, tail to head, they need to close. And eventually you can think about it as, you start from here to here, and from here to my here to the earth, and then back to my knee and back. So if we make this loop, this is a spin one, and I can play, I can dance the lambada. All these configurations that I can play, they all satisfy the sum of the spins on the tetrahedron equals 0. So out of those configurations, actually for the spin pyrocloth, when we have corner sharing tetrahedron, in that case, this large degeneracy of a single tetrahedron will make the pyrocollattice disordered at any finite, any small temperature. In this case, we have edge sharing, so this is more coupled system. There was another paper in '59, Villain, and he tried to identify the phases of the FCC lattice with J1 and J2 parameters. He identified 4 phases. I'm not drawing here the phases, you will see them later. And there are some papers in between, and then there was the next paper in '72, where again the J1-J2 has been studied using the Tisza-Lagtinger method, Lagtinger-Tisza method. This is something that Mortimer-san already told us. You make the Fourier transform of the spins, and you minimize the Fourier, the Hamiltonian into Fourier space. And he already put a few materials here that are known to be FCC lattice materials. Recently, I learned from Harald that there are many, many more of those materials. Right. And what I learned from Yasir, that quite amusingly, I would thought that the FCC lattice is one of the basic lattices in the condensed matter physics, in the crystallography. And yet, there was no systematic study of the J1, J2, J3 model, antifermi Heisenberg model. So this is a great opportunity to fill this gap. So this is what we did. We use like this Lagtinger, and this is our phase diagram. Now, the known phases were at the J3 equals 0. This is the, here I said J1 either ferromagnetic or antiferromagnetic, and the J3 equals 0 line is this line. And that line was where earlier studies were done. And what you see that introducing the J3 introduces new qualitative features. Namely, incommensurate states appear. And this is related also to what we heard from Mortimer-san, that longer range interactions, for example, introduced by Eka-Carbide interactions, can stabilize incommensurate order. This is quite complicated phase diagram. There are many, many, many phases. Those phases can be characterized by the ordering vector in the Bilon zone. This is the Bilon zone of the FCC lattice. The gamma, this is the uniform order of the ferromagnet. And this white region here is where the ferromagnet lives. Then we can have the L point. That is the 1/2, 1/2, 1/2 direction. That is the mangan oxide. And it occupies this reddish region here. And then we can have another ordering vectors around the 1, 0, 0 or 1, 1/2, 0. These are ordering vectors at high symmetry points. In addition, we have the incommensurate orders that are between the gamma point and these high symmetry points or between other high symmetry points. This is not everything what we found. We found that, for example, here, there is a so-called one-dimensional manifold. Along this line, we can put any Q vector on this, in the Bilon zone that is lying on this line here, can be a good ground state candidate. So we have a choice of from choosing different K value ground states. It's even more interesting that there are other 1D manifolds where we can do the same game. So this is a triple point between the Q00 incommensurate between the gamma and the X phase. The gamma point is here, the X phase is here, and in this phase, the Q, the ordering vector will be along this line, but its value will be determined by the value of J3 over J1. At this point, however, all the Q values on this lines will become equivalent, and any Q from this manifold can be a good ground state. Okay, this is something more interesting, that we can also play more games. We can rewrite our Hamiltonian at this point here as a sum of total squares. So if we have a sum of total square, we know that the absolute and absolute ground state will be achieved when this is equal to 0. This is very similar to what I told you about the tetrahedron, that the sum of the spins is equal to 0. In this case, there are some minus signs, so we need to revisit a little bit our spin lambda. I don't know what I need to do with my legs, but anyway. And these are the sites that are present in this equation here. The empty sides are the positive ones, and the filled sides are the negative ones. And we need to add up on all different combinations of these rectangles. Let's go further. Then at this particular point, we find that the ground state can be realized on any point on this two-dimensional manifold. And these are the so-called spin SSL spin. I forgot. This is in title of my talk. Yes, spiral spin liquid. Thank you very much. And this has been kind of observed by these people here, but not really studied in more detail. In case of Ising model, it will also mean, and also the one-dimensional manifolds means sub-extensive degeneracy. So it also perhaps linked to the talk that we had last week by Yongbek Kim. How do we understand this? So at this point, this is a point where J3 is equal to 0, J1 equals to J2. We can rewrite our Hamiltonian as sum of the spins on the octahedra that share the edge. So once we make this minimum, in that case, we will find the ground state. If we, then we can also calculate, I mean, you have this many degeneracies at 0 temperature, classical spins. You can add thermal fluctuations or quantum fluctuation. You can ask if there is any ordering vector. Indeed, there will be ordering at this 1/2, 1/2. So there is an order by disorder selection. But we have this sum of the 6 spins equal to 0. This is the local constraint. And we can write this local constraint in the Fourier space so that we introduce S of Q and some F of Q. S of Q will be the Fourier transform of these spins. And F of Q will tell us how do we need to add them together in the Fourier space so that we get this constraint back. And this is something similar that Owen and Roderick did for the Kagome lattice recently. And if we do this Fourier transform, we get the ground state condition that this equation needs to be 0. This is an equation in a Fourier space, and if we solve it, we get this surface here. Right. It is not the only surface that we can draw. There is another family of the surfaces, and that is realized if we introduce additional hoppings. We need additional exchanges up to 4th order. And if there is a very fine tuning among these J exchanges, in that case, we can also draw similar two-dimensional surfaces. These are topologically different. They can be characterized by Euler characteristic. This is chi equal -4. And here, Euler characteristic is 4 or -12, depending on actually whether we have like a space around the gamma prime point or gamma points, or whether we have this more complicated structure. These surfaces, they can be also written as a sum of full squares over some linear combination of spins. In this case, we have a 3-parameter alpha. Alpha S0, alpha multiplies the S0 sitting in the center of this truncated cube. And if we do the Fourier transform of this thing, we'll play the same game. The ground state condition becomes this equation here. And if we plot it for different values of alpha, we have this, we get these different surfaces. Could you please tell me how much time do I have? 6:30, perfect. Thank you very much. 6:30, yes. Okay. And we made a construction here in this paper in this paper, we give a prescription how can one construct such surfaces. So spiral spin liquid surfaces in for two-dimensional and three-dimensional models. I mean, mathematical construction. Next, we need fine-tuning, but spiral spin surfaces has been known for honeycomb and diamond lattice. In that case, we don't need fine-tuning. So let's see what happens on the honeycomb lattice. But before that, I would like to show you a few examples of the ordering of S of Q, because we will need it for later. This is the Fourier transform of the S of Q of the ordering vectors. So if we have a black peaks, then if we have a ferromagnet, then the weight is in the first balloon zone, and there will be some small weights in the second gamma point. This is the second balloon zone, I mean, additional balloon zones, and these gamma primes, because this is a honeycomb lattice, there are some sides missing from the center. These two weights won't be equal. But we have a weight at the gamma point, U equals 0, 0. If we put a magnetic nil state, then we will have peaks only at these gamma prime points. There will be no peak at the center. And we can also have a four sublattice order that is depicted here. In that case, the magnetic back peaks would be at the center of the edge of this honeycomb, of this hexagon here. Right. Yes, so the degenerate manifolding for stated honeycomb model, it is not a new thing. It has been already noticed by this Italian team from '79, and also Japanese people studied it. The quantum model has been studied by Jean-Baptiste Fourier and Claire Lillier and Phyllis Senzanger, and also the classical and the quantum by Mulder, Ganesh, and so on. Yeah. So in the honeycomb lattice is represented here. It is made of hexagons. Hexagons have the first J1, I mean the nearest neighbor sides are J1, the second neighbor sides are here, the J2, and the phase diagram as a function of J2 over J1 looks as follows. If J2 is equal to 0, this is a bipartite lattice, and we have a perfect Néel order. If we turn on the J2, the Néel order will persist up to a certain value, but if it reaches 1 over 6, in that case, the Tisser-Luttinger minimization will give us a minimum which is away from the Néel ordering. Since the Néel ordering in the honeycomb lattice is a Q equals 0, we don't see a peak, but it is still Q equals 0 ordering. And it means that there will be, the minimum will be along a circle that is surrounding the gamma point. This is taken from the Mulder et al. I'm taking this to compare our results later on. So this is J2 over J1 equals 0.3 is this red curve. For 0.5, when the ratio of J2 over J1 is 1 to 2, in that case, we get this straight line. The minimum will be along the straight lines in the Q space. And for 0.7, it will encompass the K and K prime point in the balloon zone. So we have a Néel phase, and then the ground state will be a particular Q point from this circle surrounding the gamma point. And after the J2 is larger than 1/2, in that case, the ground state will come from the circle, this green circle that is surrounding the K point. So this is the classical phase diagram. And recently, people have studied materials that are layered honeycomb materials. This is iron trichloride. And it turns out that in this material, because it's layered, there is also coupling between the layers. And there is a J1 and J2 and so on. Nevertheless, what they find is that it can be described, it is a spiral spin liquid. And the way how they can show it is that this is the neutron scattering taken at some small but finite temperature. And I think this would be the experimental plot of the intensity in a particular plane in the 3D balloon zone. And the other here, this is the simulation for a honeycomb lattice. And you see this shape, the circular shape where the intensity is maximal, or it is actually the system is exploring the available Q values where it can be a ground state, a low energy state. This is a slightly different, I think these are different temperatures here. And yeah, this is a comparison between experiment and theory. And based on this, they conclude that this is a nice example for spiral spin liquid. Another interesting example is the diamond lattice. The diamond lattice it is non-trivial, goes back to the seminal paper from 2007 by Doron Bergman, Alicia Margul, Simon Trebs, and Leon Balance, when they show that if we have a diamond lattice is very similar to the honeycomb lattice. The diamond lattice is also a bipartite lattice, and one can introduce the second neighbor coupling that will frustrate. And in that diamond lattice, what happens is that again there will be a region in the parameter range when such two-dimensional manifold of allowed Q values that can make a ground state will appear. These are for different values of J2 over J1 frustration. Again, I think the green points represent the order by disorder, long-range order state. Mangan scandium to sulfur 4. This is an example. This is a spinel material. The magnetic materials are the scandium atoms, and they make a diamond lattice. This is the diamond lattice here, and there is the J1 and J2 interaction here represented. And when they look at some finite temperature, the neutron scattering, again, they show very clear signature of these two-dimensional surfaces in the Brillouin zone. Namely, the system tries to explore the space available Q vectors, low energy Q vectors in the Q space, and it precisely coincides with this SSR, I mean the spiral spin liquid like prediction from the J1, J2 first and second neighbor exchanges on the diamond lattice. Right. So far, I was telling you that we were playing with the FCC lattice, and we saw that in the case of the FCC lattice, we could rewrite the condition when a spiral surface appears as a Hamiltonian being a sum of spin squares. Can we do it also for the diamond and the honeycomb lattice? And the answer is yes, we can. And this will allow us to treat the honeycomb and the diamond and whatever is in between on equal footing. So this is the unification theory. What we need to do is that we introduce these tetrahedra here. So these are tetrahedra. These are the corners of the tetrahedra, and we need an additional point that is inside the tetrahedron. So you see that we take one of the green represents one sublattice of the atoms, and the purple the other sublattice, and the corners of the tetrahedra are made from the atoms on one sublattice of the diamond lattice, and the purple is sitting inside, and we have the same construction for the other sublattice. Now we can write the Hamiltonian. We can write the Hamiltonian using local constraints. Namely, we can say that let's make such a combination of spins. Here A0 represents a spin at A0 side. This is just for convenience. So the local constraint will be that we take the gamma times A0 spin at this point, beta times spin on this point here, and alpha times B1 plus B2 plus B3. Those are those three spins here. If we square this, and we have the same Hamiltonian, same condition for the purple sublattice, and if we square this condition, then what we get is a model where the J1 is given by the 2 times alpha gamma. Alpha gamma are in these conditions. The J2 is just alpha square. Alpha is this here. The J between the honeycomb lattices is 2 times beta gamma, and we have additional JC2 that is alpha times beta. So we can parameterize. We have 3 numbers, and we have like 4 different J's. So still we can't choose arbitrarily those J values, there is one condition between them. But if we look at the honeycomb case or the diamond case, in that case, there is a degree of freedom where we can vary this parameter and we can solve this equation. So beta equals 0 means that if that for the green tetrahedron, this side is missing, or for the purple one, this side is missing, and then we are back to the honeycomb lattice, right? So it allows to interpolate between honeycomb and diamond. Now let's see we try to solve this. So these are the local constraints. And how do we solve it? We try to go into the Fourier space. And what we say is that suppose that we look for a solution where the bonds are translationally the identical bond under translational translations are having the same energy. So this is something that like Laura Maceo, Claire Lilly, and Gregor Miskic looked at in slightly different for the Kagome and other lattices. So what if we assume that all the same bonds that are pointing in the same direction have the same energy, it means that we can get, if the spin is pointing in a certain direction, if we apply O3 matrix representing a rotation of the spin to this SA, then we will get this W times SB spin. And if we apply the same operator along the same bonds, we will know that those energies, the scalar products, will be always equal. Similarly, we can define a U matrix that is for the edge that is pointing in other direction, and V for the third direction, and we choose SA and SB, the initial conditions freely. Now, if we do this, then what we know that if we have a spin at a certain site, if we move it to the delta direction, then it will be multiplied by R delta, those are the UVWs, times the SR. And we can, since R delta is the O3 matrix, that representation of the translation group, if we go, say, from, I would need 4 spins. So if we have 4 spins, then say the problems I don't have 4 spins here. So you can go from 1 spin to the second and to the third one, or you go from 1, 4th, and 3rd. So we have 2 passes that we can, 2 different paths that we can get to a certain spin. And since the value of the spin, the final spin, shall not depend on the path, it will mean that the spin which is reached at delta plus delta prime is a product of going first to the delta and then going in the delta prime direction, or we first go to the delta prime direction next to delta. It means that these two O3 matrices are commuting, and then we can ask what are the possible commuting O3 matrices. Those are represented here. And then with this ansatz, we may try to solve our solutions. And what we will get is a phase diagram where it will describe actually this UVW, they will describe a helical phase, usually, except for this particular point here. Sorry. Excuse me. Except for some particular points where we will have kind of a double helices as a solution within this approach. And also we recognize that for the diamond lattice, we recover the FCC ground-state manifold or particular, there is a mapping between the ground-state surfaces for the diamond and for the FCC lattice. Now, let's check if this picture works. So what we try to look at is that, I'm not a numerical man, so these are very naive and stupid numerical simulations. And what I take is a finite size cluster like this of the honeycomb. And what we do is that since we want to get incommensurate wave vectors, If we have a periodic boundary condition, in that case, it is very difficult to detect incommensurabilities. Instead of that, we look at the open system. If we have an open system, in that case, there are very strong edge effects. And because of that, there is a method that is called the sine square boundary condition, where the J values, as we approach the edge, decreases as sine square R over R. R is the distance from the center, and capital R is the size of this cluster here. And as we do this, as we modulate the J couplings along this radius, the edge effects will become very small. And this is something that goes back to Katsura-san and Chizahotta. So there are many people who are using this method. So if we do the minimization, in that case, for example, here J2 equals over J2 is 0.3. In that case, we get a solution where all the spins are in a plane, and this is in full agreement with our theory. In the case space, these are I have interposed the Q structure of this state and the picture coming from the Ganesh and other people's work, and we see that there is this peak here lying on the red curve that is telling us where the Q shall be. If we haven't found a ground state, precise ground state minimum, in that case we get spins pointing anywhere in the sphere, and yet the momenta are essentially in this, lying on this circle of the ground state manifold. Ouch. Okay, 0.7, this is another simulation here. They are almost, this hasn't converged precisely, but yet the spins are on the, this is a coplanar structure. And again, if we draw the expected minima, the expected minima for 0.7 are these dashed lines. In that case, we see that the Fourier transform of this thing lies on the ring curve. Okay, this is fine. 0.5, we got this double spiral. This is a special case that I was talking about. And in the Fourier space, if we do the minimization, sometimes we see that there is not a single Q peak, but there are many Q peaks allowed for the exact minimum. Okay. Right, this is the special case. This is the special case when J2 or J1 is equal to 1/2. It corresponds to alpha equal gamma in the equations. And the local constraints are, in this case, just the sum of the spins on this upper triangle shall be equal to 0. We have seen this before. This is the criteria of Anderson from the first slide or second slide. The sum of the spins shall be 0. This is like a perfect tetrahedron. So we expect to see some more degrees of freedom, the same for the purple triangle. And the force-up lattice state that is shown here satisfies this condition. The black peaks are at these points, and they lie on the ground state line of the honeycomb lattice. Now, what we are allowed to do, this is a force-up lattice order. Here, this is the tetrahedron that I'm talking about. The A, B, C, D spins, if added together, they add up to 0. This is the Fourier transform of that thing, but we can also have domains that look like this. This is A and the A prime. These are opposite looking spins, and B prime are also opposite looking. They satisfy any tetrahedron that you would draw here. It will satisfy the tetrahedron condition. So domain do not cost energy at all for this particular value of J over J2, J2 over J1. And this is represented by this that we have weight along this line in the below zone. We can do something else. We can solve the constant equation analytically using Mathematica. Then what remains is that we solve the equations that determine the spins, the sum of the spins, but then we need also accommodate that we have 3 spin components. The sum of the length of the string shall be equal to 1. And this is additional constraint that is not taken care about those equations that I have shown before. If we take that also into account, we find that all the green spins are determined by the purple spins plus the S equal 1 constraint. We can try to solve this equation, and then we end up with configurations like this here. This is this is for 1/2. Again, we see a more complicated domain structure here. and we see the peaks here, and the domain structure we saw has this type of domains. And in this case, A, B, C, D, the sum of these spins needs to be equal to 0. Okay, so this is what happens for the honeycomb. For the case of the diamond lattice, we would like also to check our theory. In the last week, and also I learned from Ludo that over relaxation is very good way to get rid of the minima, local minima. So I'm trying to find the similar structures, but apparently in this case, there are many low-lying minima that are almost zero in energy, completing a square. So I know that it is not a ground state, but it is a local minimum. So I try to run this many times, and I hope that I will be able to confirm the picture. And this is the final. So to conclude, so I have shown, okay, so the first part was the FCC lattice. We showed that for extending it for the J3 and J4, we found new physics. It is not just a stupid extension, but we find incommensurabilities. We find one-dimensional manifolds, two-dimensional manifolds, sub-extensive degeneracies leading perhaps to the fractal physics, and so on. And we have given a recipe how to construct Heisenberg models with with spiral spin liquid properties on Bravais lattices, and then we extended this local constraint picture to anisotropic diamond lattices that will allow us to combine the honeycomb and the diamond lattice. And we will, and possibly this can be applied to the iron. All right, thank you very much for your attention.
Let's thank Karlo. A very interesting talk. The talk is now open for questions.
Sorry for being over time.
You just finished on time.
Yes.
How do I get a mic to you? Okay.
Yes.
One question. So you said that in the honeycomb lattice,
Yes.
the spiral spin liquid is not fine-tuned. It just emerges.
If you have only first neighbor and second neighbor, it is not fine-tuned.
Yeah. So my question would be about, what happens. So this is all about classical phases, and then you might have order by disorder. But on the honeycomb lattice, you don't have order by disorder from quantum fluctuations, do you? So can you say anything whether these spiral spin liquids on the classical models can give rise to what kind of quantum phases they would give rise to?
Right. So this has been studied by the paper, the 2010 paper, Ganesh and other people, paramechanically. I think I haven't read carefully that paper, but probably there are some places of the K momentum where the spin wave, at zero temperature, you expect the ordering to happen. Indeed, it happens.
So it does happen. So there is ordering at zero temperature.
There is order by disorder. The spin 1/2 case, this is at zero temperature. Any final temperature you will, right. The spin 1/2 quantum case is more interesting. You will have some near-order state, then you will have a resonance of the dimers, and then you will have a dimer state where all the dimers are pointing in the same direction. It's kind of a ladder or. So that is also known.
Okay, thanks.
Any more questions?
I apologize for my obsession with dipolar interactions, but will this degeneracy that you have be lifted if you turn on dipolar interactions between?
I believe so. Yes. It's just a question of how large the spins are, what is the J, and so on.
But this could be another mechanism in addition
Absolutely.
to order from disorder.
Yep.
Any questions from the online participants? If not, let's thank Karlo and all the speakers of this session.
Thank you.